So today we will be discussing on lecture on losses in pre-stressed concrete. Okay, so let's have a brief discussion on what is pre-stressed concrete section. So how it is differing from RC concrete section. So for pre-stressed concrete section, what we do is tendons which are used as steel sections in a concrete section are being stressed previous to the concrete is being cast, and also the external loads are being applied to it. Okay, so pre-stressed concrete section is where the tendons in the concrete section is being pre-stressed before the concrete is being placed in the section. So now we will be discussing on some of the losses in the pre-stressed concrete section. Mainly, we have immediate losses and losses which are long term. So losses can be divided into two sections: immediate losses and losses which are for long term. So for immediate losses, we have elastic shortening, friction, anchorage slip. And for long term losses, we have creep, shrinkage and relaxation of the steels. So today we will be covering on the immediate losses, and we will be seeing how the immediate losses are affecting the pre-stressed concrete stresses in the section. So let's go through some of the notations which are required to calculate the immediate losses, specifically elastic shortening of the pre-stressing tendons. So here we have the modular ratio, where we know that short-term elastic modulus of concrete is taken as capital EC, and elastic modulus of steel is taken as capital EP. So modular ratio is basically elastic modulus of steel divided by short-term elastic modulus of concrete. Now AT is taken as transform area of the pre-stressed member, AC is taken as area of the concrete section, that is net area of the concrete section excluding the steel tendons. Then AP is the area of the pre-stressing steel or the steel tendons present in the pre-stressed concrete section. A is the area of the pre-stressed concrete section, which is the gross sectional area of the pre-stressed concrete section, which is equal to AC plus AP, summation of area of the concrete plus area of the pre-stressing steel. Now what we will do, we can actually transform it to the transform section. How? The area of the pre-stressing steel can be transformed to an equivalent concrete area. Okay, so how we will be going to transform it? We will be transforming it using the modular ratio. So for the modular ratio, we have AC plus M AP will be giving as A plus M minus AP, M minus 1 into AP, which will be giving as the transformed section. So while solving a problem of a pre-stressed concrete section, we can use the transform area of the pre-stressed concrete member, as well as we can use the gross section area of the pre-stressed concrete member. So we can either use AT or we can use A. Okay, so A will be giving you an approximate solution, whereas AT can be able to give an almost accurate solution to the problem. So today we will be only focusing on the immediate losses in the section. So now for calculating immediate losses in the section, while going through the problem, we also need some other notations like center of gravity for or centroid for concrete section, right? So centroid for concrete section, that is the gross concrete section. Got it? Now CGC may lie outside the concrete section as well. Now center of gravity or centroid of pre-stressing steel, which is CGS, that is centroid of the tendons. I is the moment of inertia of the pre-stressed member. IT is the moment of inertia of the transformed section. E is the eccentricity of the CGS with respect to CGC. We all know that since the pre-stressing steel will be always found at the bottom layer of the concrete section and the top layer of the concrete section, so CGS will not lie around the middle of the pre-stressed concrete section, right? So wherever the CGS will lie, there will be an eccentricity elasticity, there will be a length in between CGS and CGC. And since CGC is taken as the cross sectional centroid of the cross sectional concrete member, so CGC may lie in the middle section of the member. So now we will be seeing some of the other notations which will be denoting the pre-stressing force. So when we see pre-stress concrete member is basically seen like this. So when we are actually giving a tensile force this way, right? So this is the tendon. Okay, and this is the pre-stress concrete section. So when we are providing a pre-stress, that is a tension force in the section before the applied load is provided to the section, that is before there is an applied load to the section, what we are supposed to do? Here, pre-stressing force which is given to the tendon is taken as Pi, that is the initial pre-stress force which is being provided to the tendons using hydraulic jack. Okay, these are the hydraulic jack. So what we can say, that pre-stressing force which is the initial pre-stressing force given to the tendons are Pi. Now when the pre-stressing force are given and the jack is set and the jack is removed from the tendons, there are some immediate losses the tendons go through, right? Some immediate losses the tendons go through. So for the immediate losses the tendons go through, when the hydraulic jack is removed, the initial pre-stressing force is reduced a little bit because the tendons go through some immediate losses in their strain, right? So how much it is stressed, it undergoes a little bit of deficiency in its strain. So then there is a loss in stress due to that immediate losses. That loss in stress occurs which lead to a reduction in the pre-stressing force which has been imparted to the tendons. So after the reduction of that pre-stressing force which has been imparted to the tendons, that pre-stressing force which is remaining in the tendons after the immediate losses are called P0. Now next we come the effective pre-stressing force after the time dependent losses, that is the long term losses. So P0 is after the immediate losses, whatever pre-stressing force is remained in the tendons, and PE is the final effective pre-stressing force which is going to be effective over the duration of time, because it has been reduced after long term losses are applied to the section. Now there is a flow chart. We can see that losses can be basically divided into two parts, as I have told you, that immediate losses and time dependent losses. Immediate losses are elastic shortening, friction, anchorage, and time dependent losses are creep, shrinkage, and relaxation. So for immediate losses, let's say for elastic shortening, which is normally predominantly found in pre-tension members. So far we have an idea what pre-tension members are and post-tension members are. So for pre-tension members, the tendons are pre-stressed or tendons are stressed before the concrete is casted in the section, right? Concrete is placed in the section, the tendons are stressed before the concrete is placed in the section. For post-tension members, what is happening? The concrete is already placed and cured and hardened, then only the tendons are stressed. Okay, so for pre-tension members, the bonding between the concrete and the pre-stressing steel occurs through the bond stress. Okay, and for the post-tension members, the bonding between the concrete and the pre-stressed tendons occurs through the bearing, right? So both equally important for casting situ members, casting situ sections, we go for pretension members. Okay, and for industry fabricated members, we go for post-tension members. Now, for pretension members, we will find that elastic shortening happens immediately when the jack is removed from both ends of the tendons, right? So, immediate shortening of the tendons, that is immediate elastic shortening of the tendons, that is a loss in strain in the tendons will give rise to the elastic shortening in the tendons, which basically give rise to the drop in the initial prestress in the steel. So when initial prestress in the steel is dropped, that is being analyzed using the change in stress in the tendons, right? So for the change in strain in the tendons, we will also have to find out that the strain compatibility has been assured between the concrete and the steel. How the strain compatibility has been assured between the concrete and the steel? What we assume is whatever change in strain happened in the steel, that much change in strain happened in the nearby concrete surfaces as well, because it is an embedded section. The tendons are embedded in the concrete. For a pretension member, concrete is casted after the tendons are stressed. So there is an embedded monolithic section. So whatever change in strain happen in the whatever change in strain happens in the tendons, that amount of change in strain happen in the concrete as well. So this is where we use the concept of strain compatibility between the concrete and steel, and this is where we will be able to calculate how much loss in stress happened due to the elastic shortening. So next we will be finding out the loss in stress due to elastic shortening. So let's say the loss in stress has been given as delta Fp in the pre-stressing steel, right? So that will be equal to, as we know, modulus of elasticity for the steel into the loss in strain, that is delta eta p, right? So now delta Fp is equal to this. Now what we have understood that however the change in strain happened in the pre-stressing steel, that much amount of changing strain happened in the surrounding concrete. So we can see delta eta p is equal to eta c. So eta c we know that it is equal to Fc by capital EC, that is stress in compressive strength in concrete divided by its modulus of elasticity. So from there we can say that EP by EC is the modular ratio. So we get the value delta Fp is equal to M into Fc. So for simplicity, the loss in all the tendons can be calculated based on the stress in concrete at the level of the CGS. So if we know the loss in stress in concrete, we know, that is the whatever the stress value in concrete we know, we can get the loss in pre-stressing steel from the stress value of the concrete at the level of CGS. CGS is the centroid of the steel. So pre-tension action members and pre-tension bending members. There are two types of members which are being used as pre-tension members, action members and bending members. So elastic shortening can be calculated for both the members as well. So now we see for an action member, what is happening? The tendons are kept straight, right? There is no bending in the tendons. After the pre-stressing forces, the tendons are still kept straight, right? But there is an elastic shortening after the pre-stressing process has been happened and the jack has been removed. So this elastic shortening can be shown in this figure, where length of the pre-stressing steel has been reduced after the elastic shortening and the force has been reduced from Pi to P0. Now what we can see from delta Fp is equal to MFc from the previous slide we can see. So from that calculation we can see, if we put it in the form of force from stress, reduced pre-stressing force after immediate losses by AC, that is FC is equal to P0 by AC. So from there we can say that P0 by AC is equal to the same amount of stress has been gone by the pre-stressing steel as well. So whatever stress is happening in the concrete, the same stress is within the pre-stressing steel. So we can say that Pi by transform area of the section. Pi is the initial pre-stressing force. So we can say that Pi by initial pre-stressing force divided by the area of the cross section can give you the P0, that is the reduced Pi, reduced pre-stressing force by area of the concrete. So note that the stress in concrete due to pre-stressing force after immediate losses P0 by AC can be equated to the stress in the transformed section due to the initial pre-stress, that is Pi by AT. This is derived below, right? So now what we are supposed to say? Now we already have understood that for concrete section P0 by AC is equal to Pi by AT. Now the strains can be expressed in terms of pre-stressing force as well. So we know that strain in concrete, whatever strain is in concrete is equal to initial strain in the pre-stressing steel minus the final strain in the pre-stressing steel after the immediate loss. So EC is equal to EPI, that is because of the initial pre-stress, minus EP0, that is because of the reduced pre-stress, that is P0. So now for the strains to be compatible, we can write these strains in the form of P0 by AC EC, right? Similarly, we can write eta Pi as Pi by AP EP and eta P0 as P0 AP by AP EP, right? So from there we deduce the equation and we come up to a point where we can say that P0 by AC is equal to Pi by MAP plus AC, where MAP plus AC is the transform section area. So this is the area of the transform section. So from there we can come up to the point that P0 by AC is equal to Pi by AT, which has been shown in the previous slide, right? This is equal to this. The stress in concrete is equal to the stress in the transform section, right? So this is how we come up to the point that strain in concrete is equal to initial pre-stress which has caused the strain minus the reduced pre-stress which has caused the strain in steel. So let's let's try solving a problem regarding elastic shortening of a concrete. So a pre-stress concrete sleeper produced by pre-tension member has a rectangular cross section of 300 mm by 250 mm. It is pre-stressed with 9 numbers of straight 7 mm diameter wires at 0.8 times the ultimate strength of 1570 Newton per mm square. Estimate the percentage of loss of stress due to elastic shortening of concrete. Consider modular ratio to be 6. Almost modular ratio is normally comes as 6. Now let's say this is the cross-sectional view of the section. Okay, so we have this gross dimensions and we also have the tendons. Put 4 number of tendons in the top layer and 5 number of tendons in the bottom layer. We are having the dimensions from which the tendons have been arranged, right? So let's go for the approximate solution considering the gross section, right? So for the area of the single wire, we know that pi by 4 into diameter of the wire, which is 7 mm. So we have this. Next, area of the total pre-stressing steel will be 9 into number of pre-stressing steel tendons into the area of the tendons. Now we have the gross sectional area, that is 300 into 250. Now we have the moment of inertia, which is BD cube by 12. So VD cube by 12, which we are getting 3.91 into 10 to the power 8 mm to the power 4. So distance of centroid of steel area from the soffit. Now let's say how to find it out, right? So we are taking it as y. So we have four numbers of tendons in the top layer, right? And each is having area 38.48, and the tendons are placed at 250 minus 40 from the top, and we have five numbers of tendons. 250 minus 40, that is 250 is the total height minus 40, from which the tendons are the midpoint of the tendons or the midsection of the tendons are placed, right? Now we go to the bottom layer of the steel. We are going to find out the CGS basically. So bottom layer we have five numbers of tendons which are placed at 40 mm from the bottom of the section. So divided by the total number of tendons into the area, we are going to get the CGS, which is 115.5 from the bottom layer, which is from the bottom CGS lie 15.5 mm, right? So this is the CGS, right? Now next, what we have, the pre-stressing force. Now according to the problem, if we go that here it is written that the tendons are stressed at an ultimate strength of 1570 to 0.8 times, right? So for that we have the pre-stressing force which are given as 0.8 times the ultimate strength, that is 1570, into the area of the steel. This is stress, ultimate strength, right? So if you multiply it with the area of the steel, you will be getting the pre-stressing force, which is 4.435 kilonewton, right? This is the area of the steel, total area of the steel. So now the eccentricity of the pre-stressing force, how are you going to get the eccentricity? We said that eccentricity is CGC minus CGS, right? So this is the eccentricity. So CGC is lying in the middle of the section, that is 250 by 2, and we got the CGS, that is 115.5. So 9.5 is the eccentricity. Now since the wires are distributed above and below the CGC, the losses are calculated at the top and the bottom wires separately. So we have 4 wires at the top and 5 wires at the bottom. So we will be calculating the losses in the pre-stress in the concrete section separately for the top layer and for the bottom layer. Now the stresses at the top wires is 125 minus 40. So y is from the top. If you are going to calculate y from the top, it is 125, which is the CGC, minus 40, where the midsection of the that is this is right. So this whole is 125. So this is where we are going to basically calculate the stress, right? So and this is where the tendons are put. So now FC, how we are going to get the FC? We know that while we are stressing the tendons, since it is the tendons are at an eccentricity with the centroid of the section, the concrete section, we will be having a couple, right? We will be having a couple forces which will be acting in the opposite direction on the top fiber and in the same direction in the bottom fiber. Let's say we are taking the compressive strength which is being generated in the concrete as negative. So the compressive strength is negative and the tension is taken as positive. So for the top layer, since it is being stressed, for the top layer there will be a tension will be acting at an eccentricity E, and at a distance of yt from the top, right? So from the basically from the midsection at a distance of yt, right? So here we have the axial force, that is Pi by A, which is the initial pre-stress force, divided by A, which give you the stress due to initial pre-stress force, and this is the tension in the concrete due to the eccentricity of the steel tendons from the CGC, right? So now we have these values, we know E, we know YT, we know Pi, we know I. We are putting those values and we are getting the value which is the compressive value, that is minus 4.9 Newton per millimeter square. Compressive stress has been generated in the section, right? Next, we have stress at level of bottom wires. Okay, so stress at level of bottom wires, we are supposed to do the same thing. We have CGC in the middle of the section, that is over here, and we have bottom wires, this wires, the midsection has been considered as this. So we have, this is as usual 125 minus 40, right? So YB is 125 minus 40. We know the value of E, which is 9.5. We know PI, we know A, we know I. So we are going to get the bottom. Now see here, since the hydraulic jack is giving the force in the tendons, here we have both the axial stresses as compressive as well as the compressive stress generated due to the eccentricity of the steel tendons as compressive. So at the bottom fiber, both the stresses will be compressive, right? The forces, stresses generated due to the eccentricity as well as the axial stresses. So here we are getting minus 6.7 Newton per mm square, right? So now what we have got? We have got the loss of pre-stress in the bottom wires as well as the pre-stress in the top wires. Now loss of pre-stress in top wires, how we are going to calculate? We are going to calculate the loss of pre-stress in the top wire. Pre-stressing wire is basically modular ratio into FC into AP, right? AP we know the area of the steel. Here we are using the area of the cross section. We are getting the basically the stress in the concrete section at the level of the bottom wires as well as at the level of the top wires, which are FCB and FCT. And here we are going to get the loss in pre-stress in the top wires and in the bottom wires with respect to the area of the steel. We know that both of them are having the same stress FC, because we have said that for cross section, whatever stress is coming, for the transform section to get it, we will only have to multiply it with the modular ratio. So FCT is actually is equal to MFC for the transform section, right? So here we are going to get the loss of pre-stress in top wires as well as loss of pre-stress in the bottom wires similarly. Now total loss of pre-stress, we are going to add it, summation of top wire pre-stress losses and bottom wire pre-stress losses. From there, we know this is Pi, 435 is the Pi which we have calculated. We have this, that is the force, 12.3, right? We have basically multiplied it with the area, right? The stresses we have basically transformed it and multiplied it with the area. So we are getting the forces, right? So here we are going to get, how we are going to get the percentage loss in the force, 12.3 divided by the initial pre-stress multiplied by 100%. So here, as we can see, this is the axial compressive stress generated in the section due to the pre-stressing of the tendons, and here is the eccentric compressive strength, that is tension over here and compressive stress over here due to the eccentricity of the steel, that is the steel are placed at an eccentricity with the centroid of the concrete section. This is how we are going to calculate the stress in concrete at the level of the steel, right? So we had a brief introduction of how an elastic shortening happens and how we are going to calculate the elastic shortening in the section, as well as we are going to calculate the loss of prestress due to elastic shortening in the section, and how much loss of prestress has happened, how much percentage loss of prestress has happened, we have calculated, right? So here there is another thing I would like to discuss about, like we have already had the percentage loss. If we didn't have friction loss or anchorage slip loss, then what will be the P0? We can calculate P0 from here, right? So we already have 12.3 as the loss in prestress. We know the initial prestress, that is 435. So P0 will be 435 minus 12.3. Right? So this will give you the value of P0, which is the loss after immediate, which is the final reduced pre-stress in the tendons after immediate loss. Now, next come to loss of pre-stress due to friction. So, how is friction generated? Friction is generated in between the concrete and the steel section after the stretching has been done. So, when the steel is stretched, the pre-stress, when the steel is stretched, the pre-stress in the tendons are being induced. The concrete section and the steel at their interface go through frictional forces, for which there is a loss in the pre-stress of the tendons. So the tendons undergo a loss in strain, which basically give rise to the loss in pre-stress. So for here, as we can see that friction normally is much predominant in the post-tension members, not for the pre-tension members, because during the pre-tension member, when the pre-stressing happens, that concrete is not casted. So, but a post-tension member, concrete is already casted and hardened, and then the pre-stressing happens for the tendons. So, there is a frictional loss happens in the post-tension members. We cannot see it in the pre-tension members generally. For frictional losses, what we take, the coefficient of friction comes into play. For coefficient of friction, we can always refer to IS 1343 2012, where the values of coefficient of friction has been provided according to the type of interfaces the concrete and steel are undergoing. Like for steel moving in smooth concrete, we have coefficient of friction as 0.55. Steel moving on steel fixed to duct, these are all post-tension members. We have coefficient of friction as 0.3. Steel moving on lead, we have 0.25. Now, friction mainly depends on the following variables: coefficient of friction, curvature of the tendon, and amount of pre-stressing force. So, if this is a section, let's say this is a beam section. So, the more carved the member is, the friction will be more, right? For frictional losses, there are two components of the tendons have to be shown for the stresses. So, this vertical components is directly dependent on the frictional loss happening to the pre-stress concrete section, right? So, the amount of curvature in the tendons, the more the frictional losses happen. The more straight the tendon is, the less losses happen. Amount of pre-stressing force, the more the pre-stressing force is, the more frictional losses happens. The less the pre-stressing force is provided in multiplication to the ultimate strength, the less the frictional losses is subjected to happen. Coefficient of friction is also an important role, which is playing on the types of interfaces the concrete and steel duct is having, right? So next we are going to have a brief introduction on anchorage slip as well. So anchorage slip is mainly found in the post-tension members as well. So in a post-tension member, when the pre-stress is transferred to a concrete, the wedges slip through a little distance before they get properly sealed in the conical space, right? So when the prestress is transferred to the concrete and the wedges is slipped through a little distance, right? So what happens? Prestress is transferred to the concrete and the hydraulic jack is removed. So when the hydraulic jack is removed, the wedges where the tendons have been connected normally slips because of the pre-stressing force. Due to the slip of the wedges, the tendons slip, which basically give a slip in the anchorage, which give you a reduction in the strain in the pre-stressing steel. So that reduction in the strain in the pre-stressing steel will basically give you the loss of pre-stress due to the anchorage slip, right? So there is loss of pre-stress due to consequent reduction in the length of the tendons. So how much the pre-stressing forces are given, it is also dependent on the amount of anchorage slip which will be happening. So more the pre-stressing force given, more anchorage slip might happen, right? So now according to the IS 1343/2012, which I have mentioned before, there are different types of anchorage slip we normally take according to the anchorage system which are being provided, like Freycinet system, which is very common to provide pre-stressing force to the tendons of pre-stressed concrete members. We can find out that anchorage slip generally happen from 4 mm to 6 mm. For Magnell system it is 8 mm, and for Divi-Dag system we have 1 mm. So now I would like to say that we have a generalized idea and we already have solved one problem for immediate losses happening in the pre-stressed concrete section. For further losses, for long-term losses, we will be discussing in the next section.